Ever get confused by flipping smart pointers? Don't worry, I was there too. I was also scared when I saw these ARC, RC everywhere with these angle brackets. But today I'm here to demystify these alien names and actually conquer them. Oh, and if you're new here, my name is Paul and welcome to my channel. The computer doesn't magically have infinite amount of memory. It is the developer's responsibility to manage them. In Rust and other different low-level systems programming language, they split the memory into three major parts: the stack, the heap, and the static memory. The stack is like a stack of book, where a book represents a piece of data. The data stored here must have a known size at compile time. Like how the size of a book in the stack must be a standard and a predictable size of a book. They are very quick and they follow the LIFO manner, meaning that you can only add or remove the topmost book. The heap is another major region in the memory. Think of it like a simple cardboard box. The data in the heap have a dynamic size. You can put anything in the box, but you first have to allocate and ask for space. However, unlike the stack, it is slower and requires precise management to avoid memory leaks. You also have to clean up the box so it doesn't get full with unused data, and carefully set guardrails to not to overflow or corrupt the contents of the box. The last major part in the memory is static memory. Data with a static lifetime, which means the data that lives for the whole duration of the program, lives here. Think of it like a paper. You write some stuff down in a pen, but after the paper is unnecessary, you throw it away. You can't erase it because it is written in pen, but when the program ends, the whole sheet of paper is thrown away. Okay, now back to the topic, and you might be asking, so how does this all relate to smart pointers? Let me explain. Before diving into the topic of Rust smart pointers, first you have to get what the pointer is. A pointer is the data that holds an address to another data, just like a house address. It doesn't contain the house itself, but it tells us where it's located. However, Rust does not allow a direct usage of pointer. Instead, we have a cousin of pointers, which are called references. References are ubiquitous pointers, but with safety guarantees and restrictions. I won't get into a whole explanation. This is a whole video on its own. I'm planning to make a video about it, so stay tuned. In the meantime, I recommend checking out the Let's Get Rusty channel, where they explain the concepts better and deeper. Now, smart pointers are basically data structures that inherently points to another memory, aka a pointer, but on steroids. It gives more metadata and capabilities. There are many smart pointers available in the standard library and also from famous libraries. However, I will only talk about the common ones, including ARC, RC, Box, and Cow. The first smart pointer that I'm going to delve in is the box smart pointer. The box smart pointer is often used to allocate the memory on the heap. A use case of this would be a very large value. Storing large value on the stack is technically possible, but it might lead you to the infamous stack overflow error and inefficient memory usage, so you can store them on the heap. Another use case would be a recursive data structure. The box smart pointer is like a literal cardboard box. You have a large collection of your favorite photos, but you don't want to put them in the room, which is the stack, which is faster to retrieve. So you put them in the basement, which is the heap, which is bigger, but it takes time to reach. So as you can see on this example, we have a struct node that has a data, which is an int32, and the next node, which is an option enum of a node. As you can see, the Rust compiler crashes out, saying that recursive data has an infinite size and we should insert some indirection using a box smart pointer. This is because the compiler has to lay out struct node, but inside it is another node which contains another node, and so on. This leads to an infinite size. Now, as you can see, we wrap the next node around the box smart pointer, and also we declare the next node inside a box : new. Now, as you can see, it works perfectly. The second smart pointer that I'm going to talk about is RC and ARC. Usually, Rust compiler forces you to only have one sole owner to a value. However, when we want to, we can bypass this rule by using the RC pointer. The RC pointer stands for reference counter, and as the name implies, it holds a count for how many variables owns that data, and when the reference counts go to 0, it is automatically dropped. Arc is similar to RC. RC is not thread safe. On the other hand, Arc is, due to its atomic nature. Think of RC like a TV in the living room. No one really owns the TV, but people can watch it, but as soon as the last person that is watching the TV leaves, the TV is turned off. In this code example, we can see that we have an analogous code to the previous one, but we have two nodes that has a same next node. The Rust compiler also crashes out here for using a moved value. We can fix this code by wrapping this around the RC instead of box, and use RC new to create a new node and RC clone, and which takes a reference to a node to specify the next node. And here we'll also print the reference count to the RC node 1. Now the reference count goes up, and after we drop node 2 and 3, it goes back to 1. The last smart pointer that I'm going to talk about is cow, copy on write smart pointer. Cow is an enum that has two variants, owned, which holds an owned value, and borrowed, which holds a borrow reference to that data. When a cow instance is created and represented by a borrow value, this means that the cow reference cannot make changes to the data, as it does not own it, just like a read-only data. But if it's represented as owned, this means that the data can be manipulated. However, it is lazy, so it does not make a copy unless an attempt of modification has been made. Think of the cow smart pointer as a librarian. You can look at the books and you can borrow them, but if you want to make a change to that book, you have to ask the librarian to photocopy it, and then you can make changes to it. As you can see in this example, we have a function called makeUpperCase that takes a string slice and makes it uppercase if any letter in the string slice is lowercase. This works. However, when every string is uppercase, it returns the S to string. So this means that even if we don't need to, we are still allocating a new string. With cow, we can make this function more ergonomic and efficient by returning the cow borrowed variant, which removes unnecessary allocations. Okay, and that was all for my first video. I hope you liked it. If you want to support me, please consider subscribing and feel free to comment down below. And I hope you stay rusty, I guess.